All right, so today we're diving into a question that's kind of uh, bugging thinkers for like centuries. It's about, why does time seem to go like in one direction? Why can't we, unscramble an egg or unspill coffee?
Yeah.
We're going to be unpacking this idea of thermodynamic asymmetry in time. Don't worry, it's way more interesting than it sounds.
Oh, it certainly is a very captivating puzzle, I think. We're essentially trying to understand why time flows in one direction, when the fundamental laws of physics seem to work just as well in reverse.
Yeah, that's what makes it so fascinating. And we're going to be using excerpts from the Stanford Encyclopedia of Philosophy as our guide today. So, we're really getting into the philosophical nitty-gritty of it.
Right, and I think a good place to start is with the puzzle itself. The fundamental laws of physics, like Newton's laws of motion or the laws of gravity, don't distinguish between past and future. They're what we
Okay.
call time symmetric.
So theoretically, ball rolling down a hill could just as easily roll back up.
Exactly, yeah. From a purely physics standpoint, there's no reason why that couldn't happen. But in our everyday experience, we see time moving forward, not backward. Heat flows from hot objects to cold ones, not
Mhm.
the other way around,
Yeah.
Our coffee cools down, it doesn't spontaneously heat up.
Right, and that's really the crux of this whole, you know, thermodynamic asymmetry, right? Things in the universe tend towards disorder, not order.
Precisely. And this tendency towards disorder is captured by something called the second law of thermodynamics, which states that the entropy of a closed system always increases over time.
Okay, so let's unpack that a little bit. What exactly is entropy, and what does it mean for it to increase?
Well, entropy is essentially a measure of disorder or randomness. Imagine you have a deck of cards and it's arranged in perfect order. That's a state of low entropy. But now if you take that deck and you shuffle it, the cards become all mixed up. That's a state of higher entropy. The more disordered or random a system is, the higher its entropy.
So the second law is basically saying that things naturally tend to get more jumbled up over time.
Yeah, that's a good way to put it. And this is where the brilliant physicist Ludwig Boltzmann enters the picture. He attempted to explain this tendency towards disorder by delving into the microscopic world of particles.
So we're going from the, macroscopic world of like coffee cups and decks of cards to the microscopic world of like atoms and molecules.
Exactly. Boltzmann developed the field of statistical mechanics, which connects the macroscopic properties of a system like temperature and pressure to the microscopic behavior of its particles. His key insight was that entropy is related to the number of possible microscopic arrangements or microstates that correspond to a particular macroscopic state.
Okay, I'm trying to picture this. Can you give me an example?
Absolutely. Let's imagine a box of gas molecules. If all the molecules are neatly arranged in one corner of the box, there's only one possible microstate that corresponds to that macroscopic state, all molecules in one corner.
So that's a state of low entropy because
Yeah.
there's only one way for it to exist at the microscopic level.
Precisely. Now imagine the molecules spread out evenly throughout the box. There are countless ways for the individual molecules to be arranged, while still resulting in that same macroscopic state of, being evenly distributed. That means there are many more microstates corresponding to that equilibrium state.
So a state of high entropy has more possible microscopic arrangements, even if it looks pretty uniform at the macroscopic level.
Exactly. And Boltzmann's genius was in linking this statistical idea to the second law of thermodynamics. Systems tend towards states of higher entropy because those states simply have more possible microstates. It's kind of like rolling a pair of dice. You're much more likely to roll a 7 than a 2 because there are more combinations of dice that add up to 7.
Okay, I think I'm starting to get it. So time's arrow is essentially a consequence of probability. It's more likely for systems to move towards disorder because there are simply more ways to be disordered.
That's the essence of Boltzmann's statistical explanation. However, there was a catch, and it came in the form of objections from other physicists like Loschmidt and Zermelo.
Uh, oh, what was the problem? It was sounding so neat and tidy.
Well, they pointed out that the fundamental laws of classical mechanics are time reversible. Every process that can occur in one direction of time can, in principle, occur in reverse. Loschmidt's objection, known as the reversibility objection, highlighted this time reversal invariance of the underlying laws.
So if we could reverse the motion of every single particle in a system, it would look exactly the same as the original process, but running in reverse.
Exactly. Think about like a video of a ball bouncing. If you played it in reverse, the physics would still make sense. The problem is this creates a conflict with Boltzmann's statistical explanation.
Because if the laws are reversible, shouldn't entropy be just as likely to decrease as increase?
That's the crux of the issue. And Zermelo had another objection called the recurrence objection. He argued that in a closed system, the particles would eventually return to their initial state, which means that entropy must have decreased at some point.
So we have these time-reversible laws that seem to contradict the observed tendency for entropy to increase. What do we do with that?
That's the challenge. How do we reconcile the time-symmetric laws of physics with the clear time asymmetry we observe in thermodynamics?
Yeah, that's the big question, right? And it leads us down kind of two main paths, you know. One is to say, well, maybe there's something special about the initial conditions of the universe. And the other is to say, well, maybe there are actually laws of nature that are inherently time asymmetric.
So it's either a special starting point or like special laws. Okay, let's explore those. What about this idea of special initial conditions?
Yeah, so that's where something called the past hypothesis comes in. It basically says that the universe began in a state of exceptionally low entropy. You know, it's like our box of gas molecules all started like perfectly arranged in one tiny little corner.
Okay, so that would be a highly ordered state, right? So the past hypothesis is saying that the arrow of time that we experience, like the fact that entropy always increases, is really a consequence of this incredibly ordered beginning. Exactly. As the universe evolves from that initial low entropy state, it naturally tends toward higher entropy, just like
Yeah.
our gas molecules spreading out and mixing. So the past hypothesis is kind of an attempt to ground the thermodynamic arrow of time in the universe's initial conditions.
But if the universe started in such an ordered state, doesn't that raise even more questions? Like, why does it start that way? It seems like we're just pushing the mystery back a step.
Yeah, you've hit on a really key philosophical point here. Does the past hypothesis simply shift the problem, or does it offer a genuine explanation right? Some argue that the initial low entropy state of the universe requires its own explanation, maybe pointing to some like deeper principle or mechanism. Others contend that it might just be a brute fact, a fundamental feature of reality that simply is.
There's no easy answers there.
Mhm.
Okay, let's move on to that other path you mentioned, searching for time asymmetric laws. Are there any promising candidates out there?
Well, there are a few intriguing possibilities, but none without their own set of challenges. One place to look is electromagnetism, the force that governs the interaction of electrically charged particles.
Electromagnetism. So we're talking about like light, electricity, magnets, all that stuff. How does that relate to the arrow of time?
Well, the equations that describe electromagnetic waves are known as Maxwell's equations. And those equations actually have two sets of solutions. One describing waves traveling forward in time, and another describing waves traveling backward in time.
Wait, you're saying that the math allows for electromagnetic waves to travel back in time? That's kind of wild.
It is. The waves traveling forward in time are called retarded solutions.
Hmm.
And they're the ones that we observe in the real world. Think about ripples spreading out when you throw a stone into a pond. The waves traveling backward in time are called advanced solutions, and they would kind of look like those ripples converging on a point, as if the stone were jumping out of the water.
But we never see those advanced solutions, do we? Why not?
Right. That's the key question. The usual explanation is that advanced solutions violate our intuitive notion of causality. We expect causes to precede effects, not the other way around.
Right. It would be pretty strange if the ripples in the pond converged on a point and then a stone magically shot out of the water.
Exactly. So physicists typically just discard advanced solutions as unphysical. But the question is this preference for retarded solutions a fundamental law? Or does it somehow stem from the thermodynamic arrow of time that we've already established?
So maybe the reason we only see waves traveling forward in time is because the underlying arrow of time dictates that. It's like a chicken or the egg problem.
Exactly. It's not entirely clear whether electromagnetism itself has an inherent time asymmetry, or whether it's just reflecting the time asymmetry that's already present in thermodynamics.
Okay, so electromagnetism might be a clue, but it's not like a definitive answer. What about cosmology? Could the universe's overall evolution, give us insights into the arrow of time?
Yeah, cosmology definitely offers some interesting possibilities. The most obvious one, I think, is the expansion of the universe. The universe is constantly getting bigger, and that's clearly a process that happens in one direction of time.
So could the expansion of the universe actually be the root cause of the thermodynamic arrow of time? Like a bigger universe means more space for disorder.
That's an idea that's been explored. Some cosmologists have proposed that entropy might be linked to the size of the universe. As the universe expands, entropy increases.
But is it really that simple? Does expansion automatically equal an increase in entropy?
It's a little more complicated than that. The connection between expansion and entropy depends on what the universe is filled with. For example, if the universe only contained what we call non-relativistic matter, like just dust particles, then expansion wouldn't necessarily lead to an increase in entropy.
Oh, so it's not a straightforward correlation.
Right. However, our universe contains both matter and radiation. And the interaction between those two things, coupled with expansion, can lead to an increase in entropy. For example, energy flows from the hotter radiation to the cooler matter, and that process generates entropy.
So expansion might create the conditions for entropy to increase, even if it's not the direct cause.
That's a good way to think about it. And there's another cosmological idea that relates back to the past hypothesis. It's something called the inflationary model.
Inflationary model. Remind me what that is again?
Oh, yeah. So it's a theory that describes a period of extremely rapid expansion in the very early universe, like a tiny fraction of a second after the Big Bang. And some cosmologists believe that this inflationary period could have provided a kind of low entropy starting point for the universe.
So inflation could be the mechanism that set up the initial conditions that are required by the past hypothesis.
That's one way to think about it. However, both expansion and inflation, as explanations for the arrow of time, face a similar challenge. Are they truly fundamental laws, or do they themselves depend on some specific initial conditions?
So we're back to that same question. Are we actually explaining the arrow of time, or are we just pushing the mystery further back?
Yeah, that's really the heart of the debate. With both expansion and inflation, you can imagine scenarios where they wouldn't necessarily lead to the observed arrow of time. So this brings us back to the question of, whether the past hypothesis, with its exceptionally low entropy starting point, is really the ultimate explanation.
It seems like we're still kind of grappling with that fundamental question. But before we wrap up, there's one more area I want to at least touch on, and that's quantum mechanics. There's a whole different world down there at the subatomic level. So does quantum mechanics also exhibit this arrow of time that we've been discussing? Quantum mechanics always makes my head spin a little bit. It's so different from our everyday experience. So does it also exhibit this arrow of time that we've been discussing?
Yeah, well, that's where things get even more interesting. Like classical mechanics, the equations that govern the evolution of quantum systems are, for the most part, time reversible.
So we run into that same problem.
Yeah.
Entropy could theoretically decrease as well as increase.
Exactly. At least that's the case in certain interpretations of quantum mechanics, specifically the no-collapse interpretations. They kind of maintain that time reversibility of the underlying equations.
But I've also heard about these like collapses in quantum mechanics. What are those, and do they have anything to do with time as zero?
Yeah, the idea of collapse is a bit tricky to explain without getting too deep into the weeds of quantum theory. But essentially it refers to what happens when we measure or observe a quantum system. Before measurement, a quantum system exists in what's called a superposition of states. It's kind of like a fuzzy, undefined state.
So it's not in any one specific state until we measure it.
Exactly. The act of measurement forces the system to choose one specific state from that superposition. And this is what we call the collapse of the wave function.
Okay, I'm following so far. But how does this relate to the area of time?
Well, the crucial point is that these collapse events, as they're currently understood, are time asymmetric. They happen in one direction of time.
So could these collapses actually be the source of the thermodynamic arrow of time?
It's an idea that's been explored, but there's a problem with many early collapse theories. They kind of relied on an external observer or measurement to trigger these collapses. And that doesn't really work when we're talking about the universe as a whole, right? It's not like there's some cosmic observer outside the universe making measurements.
Yeah, that's what I was thinking. It can't just be some cosmic observer out there causing entropy to increase.
Exactly. However, there are more sophisticated collapse theories, like the GRW theory, named after the physicists Girardi, Rimini, and Weber. In GRW, collapses happen spontaneously, without the need for an external observer.
So in this theory, even a box of gas molecules just sitting alone in space would experience these entropy-increasing collapses on its own.
Exactly. The GRW theory introduces this kind of probabilistic tendency for systems to evolve towards equilibrium, but it does so without predicting entropy increase in both directions of time.
Because the collapses only happen in one direction.
That's the idea. The GRW theory is a fascinating attempt to introduce time asymmetry into quantum mechanics itself. However, even GRW doesn't fully solve the problem of the arrow of time. While it explains why entropy increases from a given starting point, It doesn't explain why that starting point had low entropy in the first place.
So it's a partial solution, but we're still left with that lingering question about the initial conditions of the universe.
It seems so. We've explored several possible explanations, from the past hypothesis to time asymmetric laws to these quantum collapse theories, and each one has its strengths and weaknesses.
Well, this has been quite the deep dive. We've covered a lot of ground, classical mechanics, statistical mechanics, electromagnetism, cosmology, even quantum mechanics. It's amazing how this one question about the direction of time leads to so many fascinating areas of physics and philosophy.
Yeah, it really highlights how interconnected all these different areas are and how deep these fundamental questions really run. The arrow of time is such a profound concept. It touches upon, our understanding of the universe and our place within it.
And for our listeners who are still kind of pondering this mystery, here's a final thought to leave you with. If we could somehow reverse the arrow of time, would we actually experience time flowing backward? Or would our perception of time remain the same? It's a really mind-boggling thought experiment. Thanks for joining us on this deep dive into the arrow of time. We'll see you next time for another exploration of the big questions.